We'll talk about experimental probability next. Experimental probability is the likelihood an event being estimated thanks to a number of experiments being repeated. In other words, we're going to be given the results of an experiment, and we're going to use those to determine probability. So, first example. After 1,000 spins of a spinner, the following data was recorded. It landed on blue 448 times, red 267 times, and yellow 285 times. We are asked to find the experimental probability that it lands on each color to the nearest tenth of a percent. So the probability of it landing on blue is the 448 times it landed on blue divided by the 1,000 times the experiment was done. And that's what the formula above says. Experimental probability is essentially equal to, that's why it's a curved equal sign and not an equal sign, because we're going to be rounding, the number of times the desired event happened, so we wanted blue, over the total number of trials. We're asked to give these to the nearest tenth of a percent, which means I do want percent answers. So to do that, you need to do 448 divided by 1,000. That's 0.448. And convert that to its decimal form, which is 44.8%. So when you divide, you get 0.448. You will move that decimal point right 2 places to say that it is 44.8%. Probability of red will be 267 over 1,000. So to the nearest tenth of a percent, when you divide by 1,000 and shift your decimal over, you'll find that the probability of red was 26.7%. And the probability of yellow will be the 285 times it landed yellow divided by 1,000 as a decimal, if you're seeing the pattern here, and this is a pattern only because it was 1,000 spins. It's going to be 28.5%. So the number of times the thing happened divided by the number of times we did the experiment, then shift your decimal point right 2 places. A marble is drawn from a bag and then put back. This table shows the results of 100 draws. So green marbles came out 30 times, red marbles came out 18, yellow marbles came out 18, blue marbles came out 21, and white marbles came out 13 times. Find the experimental probability of a marble of each color being drawn. Okay. The probability of green is the 30 green marbles divided by the 100 draws. That is 30% dead on. The next color was red. Probability of red will be the 18 red draws divided by 100. That is 0.18. When shifted over, it's 18%. The probability of yellow is the same thing. If it came up the same number of times as red, they'll share their probabilities. The probability of blue, 21 out of 100. That is 0.21, which is 21%. And the probability of white is 13 out of 100. That's 0.13, which is 13%. Why did these work out so very nicely? 100 draws. 100 draws means the number is the percent. It's a shortcut. And it only works this way when it's 100 repetitions of the experiment. A researcher has been observing cars passing through an intersection. 21 turned left, 15 turned right, and 14 went straight. Make a table and find the experimental probability of each result. Okay, so make a table. So cars did one of three things. They turned left, they went straight, or they turned right. They turned left 21 times. They went straight 14 times, and they turned right 15 times. What we need to know that we don't know right this second is what is the total number of times the experiment happened. So how many cars did this person observe going through? So to figure that out, we just need to add. 21 and 14 is 35. 35 and 15 means he's watched a total of 50 cars. So to find the experimental probability, we need to take these numbers, 21, 14, and 15, and divide them by 50. 21 divided by 50 is 0.42. 0.42 is 42%. 14 divided by 50 for our straight is 0.28. 0.28 is 28. And 15 divided by 50 is 0.3. 0.3, which is 0.30, is 30%. Okay, I didn't write it down, so I do hope that you actually listen to these videos. You are taking the number of times the thing happened and dividing by the 50 experiments here. Use the data in this table to compare the probabilities of being involved in a car accident for a driver between 16 and 25 and 26 and 35. So, we're being asked to compare the probability of being in an accident in this age range and in this age range. So the probability for the 16 to 25 range is going to be the number of drivers in accidents, so that 186,026, divided by the total number of licensed drivers in that age range, which is 1,354,729. That is definitely a calculator problem. 186,026 divide by 1354729. And this is about 13.7%. It's 0.137. Moving my decimal point 2 places gets me my 13.7. And we repeat. So the probability of being in an accident for the 26 to 35 age range is the number of accidents, 133,451, divided by the number of drivers, which is 1,584,345. When we type that into our calculator, we will get, let me see, 1584345. We get about 22.8%. No, we don't. My apologies. I typed that in wrong. I missed the 1 in front of the second number. So let me put that in there, and yeah, that makes more sense. We get about 8.4% here. It's 0.084, so 8.4%. So to compare, we would look at these and say, okay, you are much more likely to be in an accident between the ages of 16 and 25 than you are when you are in the age range of 26 to 35.